In this video, we are going to start in Chapter 8 of Griffith's book on Electrodynamics, the 4th edition. And Chapter 8 is on conservation laws. So by this time you've had an introductory physics course, so you should have an understanding of the importance of conservation laws and how we've used conservation laws. The idea is that we want to now apply conservation laws to the electrodynamics, to electric and magnetic fields. Okay, so so we'll start with the first section, and that's on the continuity equation, which we've seen before in this course, but we want to review it. Okay, so why do we start with the continuity equation? Because that's one of the first conservation laws to consider, and that is the conservation of charge. With the idea being that most people agree that electric charge is conserved. We can think of this globally, and that is the amount of charge in the universe is a constant. Right, which again kind of makes sense. This is a good assumption that the Big Bang contained everything that's currently in the universe. After the Big Bang, we only had a finite amount of charge, so no matter what reactions occur, we're always going to conserve that amount of charge. I say it's just an assumption. I mean, there are ideas like the multiverse, where maybe our universe is not the only universe out there, but for this course at least, we're going to go with that assumption and say that charge is conserved. There's a finite amount of charge in the universe. We can also consider this locally, which is a little bit more interesting problem, and that is if I have a local system with a boundary, then I can start with a certain amount of charge, Q, which is time dependent, but that charge is now allowed to flow out of my system, and if it's going to flow out of the system, it's going to flow out of the system in the form of a current. So therefore, the quantity of charge is changing, but if I account for it with the charge that's leaving the system, then that's the current. So there should be some relationship between the electric current and the electric charge. We can quantify that by saying this total amount of charge is basically the integral inside my volume of the charge density, which I can then integrate over the entire volume of the system. So that's the total amount of charge at a given moment in time. The current that's leaving, so how this charge is changing with respect to time, I can calculate as minus, because it's leaving, integrating over the entire surface of my system, the current density integrated over the entire area of the surface. Okay. So I can take those two concepts and I can relate them. So if I've defined Q with the first equation, I can take the time derivative of my first equation like so. And then that should be equal to minus the surface integral of the electric current integrated over the entire area. Now, if I use the divergence theorem, I can rewrite that second integral, the integral on the right-hand side, as minus the integral over the volume of the divergence of the current integrating over the volume. Now what I have is a volume integral on the left-hand side, a volume integral on the right-hand side, which means, if I write it out, I have a volume integral, time derivative of my charge density, plus the divergence of the current, integrating over the whole volume, and that should be equal to 0. So basically the time change of the charge should be equal to how much the current is diverging, how much it's spreading out in space. So I can, basically the only way to make this a useful problem is to have that integrand be 0. So if I set that equal to 0, then I essentially have my continuity equation, which says that the change in the charge over time is equal to minus the divergence of the electric current. So just another way of saying that charge is conserved in our local system. Okay, so that's charge. Why don't we move on and start taking a look at some other quantities, like the energy. And so this is in section 8.1.2, where now let's take a look and see how we can apply energy conservation to electrodynamics. So the amount of electrical energy we found before was the integral of the electric field squared over our volume, with some constants thrown in the front. For magnetic fields, the magnetic energy is 1 over 2 mu naught, integrating over the field squared, integrating over the volume. So the energy density, or in both cases, is related to the field squared. The electric field squared, or the magnetic field squared. Okay, so if we put that all together, the total energy is the sum of the electrical energy and the magnetic energy. Okay, so if I write that out, I get 1/2 the integral epsilon naught E squared plus B squared over mu naught, integrating over the total volume of the system. So that means the total energy density this script U is 1/2 epsilon naught E squared plus B squared over mu naught, which is basically just saying that we've got energy in the electric fields and there's energy stored up in the magnetic fields. So the total amount of energy has to be the sum of those two quantities. Okay, now let's take a look at basically the work. So for the work, basically the work it would take to push a charge around with a force. So we consider some force F, which is pushing on some charge right here. Then the work, first we have to define the charge. First we have to define the force. We'll use our standard Lorentz force. Like so. And then if we want to find the work, then it would have to be over some length. So the work would be the integral of the force over a length dl. Now this dl, that it's moved, I can actually get that from the velocity of the particle. So dl would be equal to v times the time. So if I put that in, I get a force dotted into v dt. So now I'm integrating over time, not length. That's pretty good. And I can put this into our equation. So I get q e plus v cross b dotted into v dt. Which essentially gives me two integrals. An integral of the electric field dotted into the velocity plus q times the quantity v cross b dotted into the velocity, integrating over time. Okay, so let's take a look at this. The first one is, well, let's take a look at the second integral. So I can rewrite the dot product because it's commutative. So v dot v crossed b, I can rewrite with the vector identity as b dotted into v crossed v. And any vector crossed into itself is equal to 0. So that's good. So the second integral disappears, and what I'm left with is the work is q e dot v dt. So I guess another way of saying is that we go back to the same statement that magnetic fields produce no work. The work comes entirely from the electric field. Now we could rewrite this and say that the charge is the charge density times the volume, and the charge density times the velocity is equal to the current. So I can now rewrite this statement as W is the integral over the volume, the integral over the time, E dot J dt d volume. Now if I look at the energy per unit time, dW dt, then I get the integral over the volume, E dot J, integrating over that volume. So I'm left with now basically the power is the integral over the volume of the electric field dotted into the electric current. So we'll expand on this in the next lecture and see if we can try and reduce it even further.